Welcome back to The Explainer. Today, we're diving into something literally foundational to life on Earth. We're going to explore the invisible engines, those unseen, highly intricate recycling systems that keep our ecosystems perfectly balanced, our plants growing, and our waters teeming with life. It's this beautifully choreographed dance of matter, and honestly, the way these systems sustain absolutely everything around us is just fascinating. Let's get right into it. So let's set the stage here with a bit of a mystery. What connects invisible soil bacteria, massive ocean dead zones where fish literally can't survive, and the clouds floating in the sky above us? Right on the surface, these seem entirely unrelated, don't they? I mean, one is microscopic, one is a massive regional disaster, and the other is a global weather phenomenon. But as you'll see by the end of this explainer, these three things are intimately tied together into one totally interconnected, deeply powerful system.
Act 1. The invisible engine, the vital nitrogen cycle.
To really understand this cycle, we have to ask a pretty weird question. How do plants eat the air? There is a massive irony here. Absolutely all organisms need nitrogen. It's a fundamental building block. You, me, plants, animals, we all absolutely need it to build amino acids, proteins, and nucleic acids, like DNA and RNA. Without nitrogen, there's no life, period. But here is the great irony. The atmosphere around us is packed with nitrogen gas. It's everywhere. Yet plants and animals can't use atmospheric nitrogen directly. We can't just breathe it in and use it to build cells. It is literally like starving at a buffet. It's completely unusable to us in its gas form.
But nature actually has a brilliant workaround for this. It acts as the ultimate translation system. Take legumes, for example, things like peas and beans. They have these tiny little nodules on their roots, and inside those nodules live symbiotic bacteria. It's a perfect mutualistic relationship. The bacteria get a safe habitat and some glucose from the plant, and in return, these microscopic workers grab that totally unusable nitrogen gas straight from the air and incorporate it into the soil in a form the plants can actually absorb. It's a real game changer.
Now, this translation happens in an exact sequence, step by step, all powered by specific bacteria. Step 1 is nitrogen fixing. This is where bacteria convert that N2 gas into ammonia. But since plants often still can't use that form, we move to step 2. Nitrifying bacteria step in. They convert that ammonium into nitrites and then into nitrites. And here's the absolutely crucial point. Nitrates are the usable form. That's what gets absorbed by all the producers out there to build those essential proteins and nucleic acids. Finally, to keep the whole cycle moving, we have step 3, denitrifying bacteria. They do the exact reverse, converting any leftover nitrates back into N2 gas.
To really cement this concept, let's contrast these two forces. On one hand, you've got nitrogen-fixing bacteria pulling that unusable gas from the air and pushing it down into the soil ecosystem. On the other hand, denitrifying bacteria remove excess nitrogen from the ecosystem and push it right back out into the air as a gas. It perfectly balances the fixation. It's just a beautifully elegant, naturally balanced push and pull system that sustains life without ever overwhelming it.
Act 2. Too much of a good thing. Eutrophication and dead zones.
So what happens when we disrupt that balance? What exactly is eutrophication? Well, it's defined as the addition of excess nutrients, specifically elements like nitrogen and phosphorus, to a body of water. And this happens primarily because of runoff from things like synthetic fertilizers and sewage. When these nutrients, which are normally pretty scarce in nature, get dumped into a lake or bay in massive quantities, it triggers an absolute explosion of producer overgrowth. We're talking massive, thick algae blooms.
The real tragedy of eutrophication is that it plays out like a catastrophic domino effect. First, the human-added nutrients arrive via runoff. Second, those algae blooms explode across the surface of the water, effectively blocking out all the sunlight from reaching the plants below. Third, because they rapidly exhaust all the resources, those massive algae blooms eventually die off, and decomposers multiply like crazy to eat them. Now, here is the crucial insight that a lot of people miss. It isn't the living algae that suffocate the fish. It's step 4, the decomposers. As bacteria and fungi break down all that dead algae, they suck massive amounts of dissolved oxygen right out of the water to power the decay process. And that severe oxygen depletion leads directly to step 5, catastrophic fish kills and the creation of aquatic dead zones.
The physical mechanics of this ecosystem collapse are pretty striking. When that runoff dumps all that excess nitrogen and phosphorus into the water, the phytoplankton at the top layer multiplies so densely that it forms a literal shield against the sun. The plants growing at the bottom, like sedgegrass, are completely starved of light. So the plants die, then the algae run out of food and die, and finally the rapid decay sets in, totally robbing the water of the oxygen needed by any higher marine life. It shows you how just a disruption in nutrient balance can completely, utterly collapse an entire habitat.
Act 3. The ultimate connector. The continuous water cycle.
Now you might be wondering, how do these massive loads of nutrients physically travel from a farm out in the middle of nowhere right into a local lake in the first place? Well, it's driven by the water cycle. This cycle is constantly recycling matter across the biosphere, geosphere, hydrosphere, and atmosphere. You've got evaporation, turning liquid into gas, condensation, forming the clouds, precipitation, bringing it all back down as rain or snow, and finally, surface runoff. That runoff is the real connector here. It's the conveyor belt that picks up our excess nitrogen fertilizers off the land and delivers them straight into the water to cause the exact eutrophication we just talked about.
But hey, the water cycle isn't just physical weather. It's deeply biological too. Take transpiration, for example. This is the process where water evaporates specifically through the stomata, which are basically the tiny pores of plant leaves. It's essentially plants sweating. They're actively pulling water from deep down in the ground, up through their roots and stems, and releasing it right back out into the atmosphere. Comparing the two really clears this dynamic up. Evaporation is a purely physical change. The sun heats up liquid water in a lake or an ocean, and it naturally turns into water vapor. It's passive. Transpiration, on the other hand, is completely biological. It is an active mechanism of life, literally pumping water from the soil through the plant and out of the leaves. Both processes are contributing water vapor to the atmosphere for condensation, but one is driven directly by the living organisms participating in the ecosystem. So here we are, back at our central mystery, fully connected. The water cycle drives the runoff, which carries the nitrogen, which disrupts the incredibly delicate balance maintained by our microscopic bacteria, leading to vast unintended consequences, like dead zones. Matter is always conserved. It's continuously recycled through these invisible engines of the earth. But I want to leave you with this final thought to ponder today. As our human inputs, like dumping massive amounts of synthetic nitrogen, rapidly alter this ancient, delicate balance, can these natural cycles actually keep up? Or are we overloading the very engines that sustain us? Thanks so much for joining me on this explainer. Keep questioning, keep learning, and I'll see you next time.